It looks like we somehow solved scheduling problems. Let's just say they're solved, okay? We'll see how it goes. How many people have a clash from 4 to 5 today? 2, 4. That's very unfortunate. There is the cardinal arithmetic, right? I didn't really see a better solution. So if you're super unhappy, we can have more talks about it or something. But I don't really see what to do. I'm sorry. Well, these classes are recorded. Are the other classes recorded as well? Okay, so that makes it clear, right? You're here for 2 hours, then you go away. Okay, let's keep going. I'm glad to see that everybody has a chair today, and there are some free chairs. Can everybody see the screen? Because this is as good as it's going to get here. Okay, I am recording. I'm doing everything. Okay, so today we'll just keep going, and we'll learn more about types and type theory and how to work with properties and prove them. And most importantly, we're going to talk about equality, because equality is kind of the first mysterious, really mysterious things that you see when you start to learn type theory. At least that was my experience. Here is some supplementary reading material. So these notes here, these lecture notes are not complete notes. This is just a transcription of the lecture, and it does not contain everything that I'm going to say. So I will always try to include reading material. If you look at the first lecture, well, I think here I did it at the bottom, but I think it's better if I put it at the top, is what you should be reading. And in general, the lecture notes contain links also embedded in various places, like here, universe levels. And then you can go and you say, okay, let me read this. And it's not a huge amount of stuff to read. So I recommend that you do some of this. I can't babysit you through all of this. You'll have to learn how to do it, to do certain things by yourself. And always remember that when things are not clear, then you should ask. You should come to me or to Daniel, or you should ask somebody. Or on Discord and so on. And I am now bothered by this typo here. Anyhow. So let's just keep going. So today we're going to learn a combination of things that have to do with type theory and Agda. They're sort of interleaved. I put them wherever was most natural. So we will start using the Agda standard library, which contains a bunch of things. And the way that you do that is you use the import statement, and you explain what module you would like to import. And if you also put open in front of it, that means everything that's defined in here, you can then just use. If you don't put the import, you have to keep typing data.nat.something. Okay, you have to fully qualify the names without the open. With the open, you don't have to fully qualify them. They will just get imported. You can selectively import only certain things. So using is going to, you can list and say, I want to import just these things and nothing else. This is convenient when there is a clash. If the same symbol is defined in two different modules, then you have to choose, select what you do. There are also other options like hiding and renaming, and you will see those, but I'm not going to go through all of them. You will see them used. And to learn more about modules, I think that the documentation is fairly clear on what the modules are and how they work, so you can learn the basics of the modules. And then the name modifiers, which is actually just the continuation of this, tell you how to do this renaming and how to do using and how to do hiding and all kinds of things. So the documentation is there, the pointers are there. If it's not clear, ask. Okay, so another one here is, just this is useful to know where it's hiding. There is a module called function, which contains things like the identity function and function composition, so that you can use function composition. I don't think I actually need this here, but I included it anywhere, just to show you where it is. When you work with this in your editor, oh, where was the bug? Here. There we go. When you work with this in an editor, when you import something like this, you can always go onto the definition of something. Like suppose you want to know how they defined composition. I move my cursor here, and then in Emacs it's option period. I think in VS Code it's F12. Is that correct? Does anybody know? F12, so go to the definition. Yeah, okay, so you press F12, which is the go to the definition. It'll take you to the file. So now I'm in the standard library. This is the source codes for the standard library, base agda functions. And it's showing me how they defined composition. And there's lots of blurb here that's super confusing. But this bit here, okay, is kind of okay. It says f composed with g is the function, which, okay, this we will learn today. It's the function that takes x to f of g of x, okay? So nothing surprising there. It's also very, very useful to learn how you go back, which in Emacs is option comma. You go back where you came from. And in VS Code, it's control minus, if I remember correctly, okay? So if you're going to spend any time working with an editor, which you are, you better learn how to use the editor. Okay, so I will use this repeatedly today. We'll go and we'll look at the definition of something and try to understand what they did in the standard library. Okay, we always have to start a module. The module name has to be the same as the file name, so this is it. And let's begin by just looking at a couple of definitions of extra definitions of types. From programming languages, you know that programming languages have types, and these are called simple or non-dependent types. And later on, we will see dependent types. They're not called non-simple, and they're not called complicated. They're just called non-dependent. Okay, so let's try a couple. So for example, here's a type which is called the unit type. If you are in C and Java, this would be called void. It's a little bit of a misnomer in C and Java and C++, because this type is not empty. It contains one element. It also contains one element in Java and C++. It's just that you can never name that element, but it's there. And it doesn't have to be ever passed or mentioned because there is no need for it. But it can be useful to have the ability to have a type that has precisely one element, and it's called the unit type. In Agda, it's written as, this is probably better. In Agda, it's written as this true top. This is typed as top. Okay. It also doubles as true, the constant true. Okay. We will see this next time when we speak about propositions as types. But already today, we're sort of slowly going in the direction of learning that logical connectives are just like type constructors. And so this is our first example where we see that a type with one element can also serve as the constant true. So I called it star here. This data type is also defined in Agda. So any questions about this? This just means top is a type, and it has precisely one constructor called star. So when you do definitions by cases, Agda will say, well, you just need to define what it is for star. Right? So for instance, if I say, okay, I'm going to define a function from top to natural numbers, like this, and then I say, key caster, we want key caster. And then I say, please show me, consider cases for x. It says, well, you just have to define the star. And then I say, well, okay, whatever, something. Yeah. So I can do that. If you look at what happens in the library, so in the standard library, there's a type called unit. So if we go and look at it, the definition is different. It says, instead of saying, so let me show you both. This was our definition here. It's an inductive data type, which has exactly one constructor. and here it's called a record. So we will learn about record types next time, so I'm not going to stop here for too long. But this one is slightly different because it says it's an empty tuple, more or less. It's a tuple of 0 things. So it's not defined the exact same way. But both of them work. For technical reasons, this one works slightly better. But the point is, this is already defined in the standard library. So we will learn how to use the standard library as much as possible. Then we have the empty type. The empty type, how do you define the empty type? Which also doubles as falsehood. So its symbol that is used in ACDA for it is just bottom, \bot. Well, the empty type is the inductive type that doesn't have any constructors. Because it doesn't have any constructors, it's going to be fairly empty. Yes. So in this case, you just write a funny definition where you say, well, I'm defining a data type called bottom. It's going to be a set. It's going to be type. So set is a synonym for type in ACDA. Where, and then underneath, you have to list the constructors. So you don't list any constructors, and then there are 0 of them. It's useful to have the empty type as well. How do you define a function from the empty type? Okay, so now this is interesting to see, because now, there were some people in the exercises. This is something I went over pretty fast. If you want to make a hole in ACDA, you put the question mark. Okay, wherever you want the hole to be, you put the question mark. You can put it here if you want to. Okay, so now it says, okay, you have 2 things. You have to tell me what this type here is supposed to be, and you have to tell me the definition of G. So wherever you want the hole, you put a question mark. Don't try to do this, okay? Don't try to type the hole by yourself. It works sometimes, but most of the time it kind of breaks. So now, if I say, please consider the cases for X, well, there are 0 cases to consider. So what will ACDA do? Well, maybe it will delete this line because it doesn't need any cases. Well, that would be a bit radical and sort of surprising. So it has a different notation, where it puts these parentheses like this, and it says, this just means, this parenthesis means, here we don't have to consider any cases. Okay? And the way, I never type these parentheses by myself. I never know how to do it correctly. I always do it through the interactive mechanism. So use the interactive mechanism for ACDA, your life will be easier. So here you just say, okay, I have an X, consider cases, and then ACDA is happy to say, no, you don't actually have to consider anything. And let's check what the definition is in the library. So in the library, the definition is exactly the same as our definition. So there's, in fact, a little bit of a clash here. And because of this clash, I don't want to, I mean, it doesn't matter because I won't use the empty type too much, but it's better to do it, to rename. I will just rename my version so that it doesn't clash with the other one. Oh, now it does, okay? So you see now that I renamed it, it doesn't know what this is. I have 2 options. I can say use this type, and I fully qualify it. I say data empty bottom, but there are other occurrences of this, you see, so I'm not going to change all of this. So instead, what I'm going to do, bottom, where are you? Okay. Instead, what you do, so you don't have to do that, is I'll say open. So that will not only tell ACDA to use this module, but also to just directly import all the names that are defined there. And if we look at what we imported now, see, we imported this. So now it knows what it is. And also here, we imported this function, which is a function which is, well, it's written in a funny way, but in logic and sets in the first year course, I explained that there is exactly one function from an empty set to any other set. This is what this is. It says, given any, well, we'll learn this today as well. Given any universe level W, if you have a type called whatever in the universe at level W, then you get a function from bottom to whatever. And there are 0 cases to consider. Any questions? So that's the empty type. Okay, so the next one that we should look at are disjoint sums. Now the disjoint sum, this time I'm not going to define it. We will go directly to the definition in the ACDA standard library, which is here. Okay, so here you see the ACDA library is kind of a complex thing. You never just see the definition. There is black magic, then there's a bunch of opens, then some variable business that we haven't learned yet. Then you see the definition. Okay, so this definition I think is probably better if I just explain what this is. So what is a disjoint sum? So disjoint sum is not to be confused with unions. So if you have two sets, say A and B, like this, well, everybody knows what the union is. The union is going to be this thing here. And in particular, if there is a lot of overlap here, each element from the overlap is only going to appear once. So when you have a union, if the sets are equal, so for example, if you do A union A, you will get precisely A. A disjoint sum is different. The disjoint sum takes these two sets apart. So it says, no. I want, even if they overlap, I want to consider a copy of A and a copy of B so that they don't overlap. So how do you do that? Well, if you have an element in here that appears twice, then it should appear twice here, okay? But I can't write XX because then it's the same element. So instead what you do, you tag it. And the way you tag it is you just write some symbol called constructor, which in Agda it's called ing1 of x for this one, and this one will be ing2 of x for this one. Okay? And in general, if you have an A here, you get here an element ing1 of A, and if you have an element B here, you get ing2 of B. So this is because you can think of ing1 as an inclusion of A into A plus B. That's where the ing come from, injection, you're injecting it. And ing2 of A, of B, there's no need to do that, of B goes into A plus B. So written as, this is also called a disjoint union, and it's written like a disjoint union, but it's also called a sum. I prefer to say sum. So this is a super useful concept in programming because it appears in data types. Sometimes you have to consider you have a data, and it can be one of two kinds, or it can be one of 7 kinds. You know, like your store is selling shoes and T-shirts and wigs. Okay, so then you would make a disjoint sum of 3 data types: shoe, shirt, wig. And you would tag each one, and then that brings some order to your programming. So this is a very useful concept. It's more basic than the union, I think. Here is the definition. So let's read the definition. So first of all, they have this funny A appearing. So this funny A, if you say, what is this? It says, look, it's up here. This is a trick where in Agda you can say, if you see a variable A, just assume that it's of type that has type level. If you see a set A, just let's take, let A, whenever we have a little a, it's going to be a level. Whenever we have a capital A, it's going to be a type at level A, and so on. So they don't have to keep repeating here. They don't have to write here that A is a level. So, but anyhow, if you ignore that, what it says is this. It's a data type, and you take a set A, you take a set B, or a type A, type B, and then what you get is a set, and this is still the business with universe levels. So if this one is at level A and this one is at level B, then both of them together will be at whichever level is larger. So this thing here is the maximum of 2 levels. So if you have a type at level 5 and a type at level 7, when you make the disjoint sum, you will get something at level 7. You don't have to pay attention right now to these universe levels too much. And then it says, well, for every x in A, there's going to be an element. ing1 is a map which for every x in A gives you an element in the sum, and similarly for B. Questions? We'll see how this is used. It'll be more useful once we see it used. Now, here's the thing. The Agda library is kind of huge, and sometimes you don't know what to actually import. So I imported here data sum base, but if you look at the files, there is data sum contains algebra, instances, properties, and this is all about sum. So in fact, there is another module that you could have included. Which, okay, we will see that later, that it's better to just have data sum like this. But if you do data sum, so this is, very many of these modules have a base, which is just a basic definition. And then if you delete base, then you get something that kind of includes everything. So you see, now this one starts including stuff. Like it includes stuff from base, but then it puts in some additional things and so on. So here I just included something that takes you directly to the definition. The standard library, using the standard library takes a little bit of exercise. Okay, so sort of dual to sums are Cartesian products, which of course you know very well. Cartesian product, right? A cross B is just the type or the set of all ordered pairs, x, y, where x is in A and y is in B. So that's another type, but if we look at its definition, we will see that it's done in a way that we don't know right now what to do about it, because it's still, again, a record type. So it's defined down here. A cross B is this sigma type, whatever that is. So that's a topic for next lecture. So we're not going to do that now, and we will avoid using products. Another type which is useful for programming is the option type, which I hope, let's see, who here has been subjected to courses by Mattia Prittner? Okay, and who has been subject? So ISRM, have you all been to my classes on principles of programming languages?
Yes.
Yeah, okay. So you cannot claim to not know what the option type is, presumably, right? Because we saw it in OCaml, and of course you remember everything from 3 years ago, don't you? Yeah, okay. So here we go. Let's remember what it is. It is often useful to have a function which either returns a result or it says I didn't find anything. So you want a function you want a value that signifies undefined or was not found or no value. So how do you do that? Well, in some languages, like in Python, this is just the constant none. You just say none. You return none when you want to say I didn't find anything. This is not exactly a good idea, because what if you found none? How do you distinguish the different, like suppose you're searching for something in a list, okay? You're searching, okay, if you find it, then you say, okay, I found it, I return it. And if you didn't find it, you return none. But what if you found none? How can then, I mean, this is ambiguous, right? Are you not supposed to search for none? I mean, it's just stupid. It's the wrong way to do it. So the right way to do it is to define a new type, which then carries the values and the additional value none or nothing. So it's defined like this. This is my copy, and then there is one in the standard library. So if you want to be able to say I either have an element of A or I don't have an element, then you define it like this. You say there are two constructors, so we're going to write just, well, the apostrophes will go away when we use the standard library. So we'll say just, for instance, just 7 means we found 7. Whereas nothing means, well, we didn't find anything. So now you can distinguish, because if somebody returns nothing, that means they didn't find it. But if they return just nothing, that means they found nothing. There's a difference between finding nothing and finding nothing. See, even English can't handle this business. Does Slovene handle this business? Yeah. Našli smo nič, nismo našli ničesar. See? That's why we have cases in Slovene. Okay. The maybe type is defined in Agda, and once again, this is just the bare maybe, which defines just this thing. But of course, you can do. I would recommend opening. If you are going to use maybe, you use data maybe, not the built-in one, because this one has more stuff in it. It imports here like things like that. It just imports a bunch of things, and so you suddenly get a lot of stuff related to maybe. Okay, Another type to review is, or to talk about, is the function type. So this you would hopefully know from functional programming, but also just from mathematics. Well, this is quite simply the type of functions from A to B. So the elements are functions from A to B. Now, what is worth saying here is that in AGDA we use the lambda abstraction for defining functions, and I would hope most of you have at least seen this before. In mathematics, so it is common in mathematics to define a function like this. Suppose I have a function r to r, and I say, well, okay, this function takes x to 2x squared plus 3. So this is one way to write it. So it's a function rule, right? And I hope you've seen this before. And then now many programming languages have notation that allows you to write this down. So in AGDA, it's lambda x arrow, and then 2x squared plus 3. And in Python, it's lambda x colon 2x squared plus 3. And in OCaml, it's fun x, this one, 2x squared plus 3. And in Haskell, it's backslash x 2x squared plus 3. Now, why is it backslash? Because it's the character that in the ASCII coding table that most resembles a lambda. So it's just a notation for functions. Now, AGDA has this notation for functions in AGDA, allows you to do things like distinguish cases, do case analysis, and so on. And I think there is a pointer here. This is one of those examples where it's pointless for me to try to write down this in the lecture notes. The lambda abstraction in section. So first of all, you have lambda abstraction in the documentation to AGDA, which is not too long, but you can read it. But then this one, the programming language foundations in AGDA, has a nice introduction as well, where you can read a little bit about lambda expressions. Okay, so I don't want to waste too much time on this because we have more serious things to do. But this is something that you should familiarize yourself with. And if you've never seen it before, then again, come and say, okay, this is really confusing. And I think rather than spending a lot of time on this in the classroom, it's better to just do it sort of one-on-one when needed. So don't be afraid to ask, please. Okay, so now we come to the next concept. So the things we were describing here are, well, what is called simple or non-dependent types. And this is like a fixed type, like natural numbers, Booleans. But in mathematics, all over the place, you have a different kind of thing, which is like, in mathematics, you don't speak about types, you speak about sets, but you might as well speak about types. And if you say something like R, that's a non-dependent set, so just a set. But strictly speaking, if I mention an interval, suppose I say something like, consider f from A, B to R. Okay, so first of all, here, probably everybody could guess that what I really meant was to say, let A and B be real numbers, and A is less than B, because otherwise the remainder looks funny. So what is this business here? Is this a set? Well, yes, it's a set, but it depends. So the point is that this set depends on A and B. For instance, if I ask you, is square root of 2 an element of AB? What's the answer? Is the answer true? No, you cannot say that it's true. Is it false? You cannot say that it's false. The answer depends on what A and B are. So you can always detect these dependencies when you say, aha, if I try a fixed element, is it in there? Well, if the element is fixed, then of course you might have a hard time telling, right? Sometimes you can, if you make the element depend as well, then you can answer. Like for instance, if I ask you, is a plus b over 2 an element of ab, then you will say, yep, it is. But that's now because they both depend, so they work together. So this is a dependent type or dependent set because what its elements are depends on some other values of some other set or type. This is extremely common in mathematics. For instance, in algebra, when you say something like, suppose you say r to the n. R to the n is not just a set. It really depends on the n. What precisely this is depends on what the value of n is. And there are lots and lots of other examples, and dependent types are an extremely powerful mechanism. They are so powerful that you can embed all of logic, everything in dependent types, and this is precisely what we're going to do. We're going to use dependent types all the time. Now, one way to imagine these types, for instance, like this, would be to say, okay, so what is this really? Well, you could think of it as some sort of a function. So now that I can use the Agda notation, I can just put like an underscore here, which maps from natural numbers to sets. So that's our first view of a dependent type. So it's a function from somewhere to sets or from a somewhere to types. So in general, a dependent type, it's also called a family, either of sets or types, is something which maps from a type, so this is called the indexing set, to sets or to types here. So I'm interchangeably using sets and types. So this is called the indexing set or type. So in a way, you collect all your possibilities together into a function so that you see exactly how it works. Let me just really convince you that this is really everywhere, all over the place. So suppose you're sitting in a mechanics class and somebody says, we have a point in the three-dimensional space which is moving in time. So just some basic dynamics. You have a body mass and it's moving around in time. So what is this moving around in time? Well, one view of it is that it's a point, right? It's natural to think of it, I have a point in space, so it's a point. But how do I say that it's moving in time? Well, which point it is depends on time. Huh? So these sorts of dependencies are all over the place and you don't even notice them. But you can always, the good way to think about them is that they are functions. So if I have a point in time, let's see, so point. So a point in R cubed is just an element of R cubed. But a point moving in time in R cubed, well, that's a different thing. That's just going to be x. And now what is time? So whatever time is, it could be an interval, it could be real numbers, and it goes into R cubed. So the dependencies appear not only in types, but also in values. When you have some value, like the coordinates of a point, they may depend on other parameters. This is really omnipresent in mathematics, and it's a very basic structure of all the arguments that we make and constructions that we make. So this is something that we want to look at, and want to look at examples of how this arises. So let's have a look. Okay, so there's a little bit of text here. Any questions? So let's go and look at the examples. So first of all, let's immediately come back to this example of a point in time. So this one is just an ordinary function, okay? But let me give you one that isn't like that. So suppose I have a family of intervals. Well, the family of all closed intervals. family is just a synonym for dependent type. Let's write it down. So the family of all closed intervals, we would write it down like this. I'm going to use the underscore notation for Agda. So what does it depend? A closed interval depends on the endpoints. So here I'm going to have two endpoints, A and B. And I'm writing down my indexing set. And I also require these intervals to be non-trivial. So like that, to set. So this is how you can think of the closed interval, and this is the indexing set. It's all ordered pairs of numbers where the first component is strictly less than the second component. So now I have a family. I can have a specific example. For instance, 3 square root 20. Okay, so that would be an example. Now, I can have a dependent function, and an example would be the midpoint, which I mentioned earlier. Well, what is it? It's a plus b over 2. So what is this? So this is now an element of ab. But now the function, see, now let's try to write what this is doing. So this here is my indexing set. Let's write it as I. What is this midpoint business? Midpoint is a function which maps from where to where. Well, it takes the endpoint. It does not take the interval. It takes the endpoints. It knows what it cares about is what are the A and B. So it takes the endpoints and gives me a result where? What's the result? Where does the result land? Well, it lands in the real numbers, but you're just lucky that all of these are contained in the real numbers, so you could give me that. So you could say the union of them all, but that would be super ugly and really just not something that we want to do, because that would be embarrassing. So what we really want to say is, here, this business here is that we take an element, from I, so we take the two endpoints, and then we land in this interval. So this is what we call a dependent function. Oops, why am I writing it like that? So a dependent function is just like a function, but the codomain depends on what the argument is. So the point is this. The codomain depends on the argument. That's why it is dependent. So let's compare this to something where this doesn't happen. So if you have something like sine, okay, the codomain is fixed. It's always real numbers. But if you take the midpoint of an interval, you will land, well, you could say that you land in the real numbers, but what is really important to you if you're talking about midpoints is that the midpoint will land in the interval that it is a midpoint of. So you want to say something like that. And we have, in fact, used these functions already in last hour. When we were writing down definitions, we were already using them. Why am I mentioning them? Because this, in mathematics, is called product. This is just the product of a family of sets. Let's compare. So let us recall this. If I have a family of sets, so which is a map from an indexing set to the class of all sets, and then what is this if I write this? It's usually written like this. Well, it's the set of all maps F, which map from where to where? Well, from I to somewhere, and in set theory we usually do the ugly thing and take the union, because in set theory we're not afraid of unions. We're only afraid of unions in type theory. So satisfying what? Satisfying that for all I in I, f of I must be an element of AI. Right? This is the definition of the product of a family of sets in set theory. One of these things is called a choice function. Why is it called a choice function? Because for every little I, it chooses an element from the corresponding set AI. But this is now the same thing, only that here I insisted that I need a large codomain that I'm going to land in, right? But I don't have to do that. I can take as the basic notion, okay? So this, instead, I can take as the basic notion that I can have a function whose codomain depends on the value of the argument. In which case, I would write this, well, how will I write this? Well, I will say, okay, we're going to map from I to where? Well, I want to say we're going to map to whatever this argument here was. So I decide to name it. So I give it a name, and I say f takes, its domain is I, capital I, and now when we apply it to the little I from the big I, we will land here. And we take this as a basic notion, and we forget about this union mumbo jumbo, which is not really necessary. We can just work like this and take dependent functions as basic. I will point out the use of basic functions in the examples, and I think that will be then, that should help. Okay, it's already 3 o'clock. So where are we? Okay, so let's just do one example. Okay, one more type, and then we have then we're going to have a break. The last time we defined, just to give you an example of an honest dependent type. Okay, so last time we defined the natural numbers, but suppose we want to define this. Given a natural number n, I want to define a type which has n elements. How do I do that? In mathematics, you would just say, well, just take all the numbers that are less than n, and you'll get n of them. So it would be a subset of the natural numbers. But we want to do this in an inductive way. So we would like to proceed. So let's see. The idea with the natural numbers was you have a 0, okay? And then you have a successor. You have a successor. Given n in n, you get a successor of n, which is again in n. But this generates infinitely many numbers. We need to be able to count how these things work. So a similar idea will work. We're going to say, well, let's read the definition and try to understand it. So what this says is, I will ignore the apostrophes again, because they're there just so that I don't clash with the standard library. So I'm not going to pronounce the apostrophes. So let's try to read this. This now says we're going to define a function from natural numbers to types or sets. So fin is a dependent type. Fin will go from natural numbers to set. So it's dependent. It's dependent. We also say it's indexed by n. And how does it work? Well, we need the constructors. So let's read the constructors. So the first one says, for every natural number, 0 is an element of fin of successor of n. So if I wrote this as a rule, it would say, if I have a natural number, n, then 0 is in fin of successor of n. So this is kind of similar to this, but, so this is a 0 prime, okay. But it's counting, it's keeping information about what the size will be. So if 0 is in it, then the size shouldn't be 0. That's why this is successor of n. And the other one says what? The other one says, if I have something which is in fin n, then I get something in the successor, and this is called successor. So let me write this one as well. So this one says, okay, we're doing things of size. We have an n. We'll just see what the size is. We have n. And then we have I, which is in fin n. So suppose I already have an element in fin n. Then I can form successor of I which is going to be in fin successor of n. So these are the rules. So why do these rules generate the right thing? How do you see that? The best way to do this is to go and generate them. So you first ask, what can I put in fin 0? Well, is there any rule here that allows me to land in fin 0? This rule wants me to land in fin of a successor, and this rule will also have a conclusion which is in fin of a successor. So there is no rule for anything that will be of type fin 0, so this one is empty. How about fin 1? Well, fin 1, because 1 is the successor of 0, yeah, I could use this rule if I plug in n equals 0. If I plug in here n equals 0, I will get that 0 prime is an element of fin of successor of 0. So this one contains 0. Okay? Now, I could also try to use this rule to generate another element of fin 1. Well, in that case, I would take n equals 0. So I would say, okay, so if I want here to get f fin 1, I have to take n equals 0. But then I need an element of fin 0, but there isn't one, so I can't do that. So this rule does not apply. I'm done. Fin 2. Fin 2. Okay, I can use this again because I can put n equals 1. So I will get this element because fin of successor of 1. Okay, but now I can do this one, see? Because I can say, hey, I could take n equals 1. So if I take n equals 1, I will get fin 2 here. And so I will get another element called successor. And this I is something that comes from fin 1. Do I have anything in fin 1? Yes, I have this guy here. And that's it. So what I see, what happens is, every time, at each next level, first of all, I get 0 prime because of this rule. I just get it directly. But then, all of the previous level generates, by applying successor, generates the next guys. So these are i's like this. Think of it like this. So every time you get one more, you get a 0, and then you get whatever you had in the previous case, but with successor in front. Because this is what this is saying. Take whatever you had in the previous level, apply successor, and you will get something at the next level. So it's generating the correct thing. It's generating fin 3 has 3 elements, fin 2 has 2 elements, and so on. Mysterious? Yes, I don't know. You will tell me if it's mysterious, but this one works. Yep.
I have a question.
Sure.
For the second step, where you do, why can't you use the first rule?
For the second step, in fin what? Fin
2.
Okay. What is the question?
Why can't you always use the first rule?
Okay, so the question is, can I use rule number 1 to generate this element? Is that the question?
Yes.
Okay, the answer is, I have no chance of generating this element using rule 1, because rule 1 generates this. This is not of the form successor of something. You see? If I use this rule, the conclusion will be that 0 prime is an element of something.
But you could use that rule.
But I did use that rule, and I got this one. If I use this rule, I get this element.
So if you use it again, you get the same element. So
Yeah, of course. Oh, yeah, okay, so that's the question. Well, if I use it again, I get the same element, yes.
And that's why you don't use it again, because nothing changes.
Well, would you like me to use it again? I can use it again. I will use it again. Oh, look, I got the same element.
Yeah, what I'm
Yeah.
asking is,
Yeah.
does ACTA know not to use it again?
The ACTA doesn't actually try to physically generate these elements. So it's a kind of a pointless question,
All right.
right? It's not trying to enumerate all the elements, because as soon as it gets to an infinite type, that's going to be a very futile exercise. What is important for ACTA and for understanding is how okay, so this is like, okay, so here's a bit of philosophy which is more important than it appears. The thing that matters is not the collection of the elements that we generate. The thing that matters are the rules of generation. The rules of generation give structure. The collection of the elements, once generated, carries no history of how you got there. You just have a big bag of stuff, and you don't know how you got there. It's forgotten. If you're lucky, you might be able to reconstruct for each element some way of why you got that element. But that depends on what the rules are. You have to be lucky for that to be possible, because the rules could be such that you can get the same element in many different ways, and then you won't know. So the important business is always the rules. The rules are the structure. The structure is what matters in mathematics and everywhere else. It's not just bare collection of stuff. So it's a good thing that you ask this. How do we generate these elements? What happens if we use the rule again? It's good for your intuition as to what will happen. What will the type look like? Of course, you have to think about the collection of the elements. But what I am emphasizing is, at the end of the day, you really have to, the thing that will direct you is what the structure is, not what the collection is. So this is a very important difference between type theory and set theory. The view of set theory is, there is a universe of stuff out there. We came to the beach. There are lots of grains of sand, pre-existing. Now we can mold them into whatever we want. So that's the set theoretic view. You make your sand castles. And the type theoretic view is not that. The type theoretic view is, Lego sent you a booklet that shows all the different blocks that you could use. Now, that gives you the rules of construction. Once you know what the blocks are, you know how you're going to construct your castle out of the Lego. Whether you can, now of course you also need the supply of the Lego blocks, of course, right? And the more you have, the more you can build. But in one case, in set theory, we think of the mathematical universe as a pre-existing totality of things, which can then arbitrarily be collected into collections called sets. In type theory, we think of a theory of constructions. We give rules for constructing things. We keep giving rules, right? We give rules, and then we play according to the rules and see what we get, what constructions we get. So it's a different view. These two views enrich each other. They're not opposites of each other. They enrich each other. Yes.
I just want a funny way to explain this.
Yes.
Which is the etymology for mother and father. For matter and pattern come from mother and father. So matter is like set theory, where you presuppose matter, and then you don't have any pattern, and then pattern is like the type theory where you don't have any matter, and they imply each other kind of. Yeah.
Okay, so if I understand you correctly, it's maybe a little bit to what I was explaining, that you can, there is a difference between having just the bare collection or building material that's available to you, and then imposing some further structure on it, or how you got there, and how it was built, or what its role is, or what's it doing, right, in relation to something else. Okay, thank you. 15-minute break, which we severely need. So we meet at past. Okay, looking at the time, I probably have to switch gears a little bit. And we'll try to focus more on the ideas and the overall structure. I'll try to get in as many details as I can, but we'll see how it goes. Am I recording? I am recording. Okay, so if you start freezing, tell me. I can make it like this, maybe. So let's look at an example of how you might use all this stuff, because we here had a type which has exactly n elements. So the way to imagine fin n is that it contains 0, successor of 0, successor of 0, and so on. But once you get, then it stops, you see. Whereas natural numbers just keep going, the types, the parameter, right, because it's a dependent type, this parameter is controlling how many successors you will be able to apply, and then after that it'll be over. Okay, so let's have a look. Now, suppose you have the following simple example of searching. This is the most basic programming exercise. I take, so first of all, I have an n. Suppose you have an n. And now I have a predicate p, which maps elements of fin n to bool. Naively, you can think of fin n, naively, okay? Think of it as numbers from 0 to n minus 1. But I will put this in quotes. The important thing is that fin n contains n elements, and they're written 0, successor of 0, and so on, but we might as well think of them a little bit like this, except they're not really natural numbers. They just look like natural numbers because we use the same names for constructors. So now, if I have a predicate, so this is a function which for each element of fin n returns true or false. I might try to find a k, so find a k in fin n such that p of k is true. This is a very basic exercise, right? How do you do this? Well, you scan fin k, and the first one that works, you just return it. So if you define this function in Python, it might look a little bit like this first one here. So this would be idiomatic Python. You would say, okay, well, in Python we don't have the fin n, so we're just going to search numbers from 0 to n minus 1, which is range n. You just, with your loop, you go through 0 to n minus 1. If you find it, you return it. But if you get out of the loop, you return none, because you didn't find it, because maybe it's not there. Maybe p is false all the time. So how would you do this using the types we have now had? So what would this find look like? Well, it would have to be something like find. Let's try to write down its type. It'll take a natural number and then it'll take a p from fin n to booleans, and then it'll return. It has to, what will it return? Well, in Python, it either returns a number or a none, but as we discussed earlier, this is really the case of maybe, so it'll be the optional type maybe of fin of n. We want it like that. So it will return nothing if we didn't find it, and it will return just k if it found k. So let's write down this function just as an exercise. What will it look like? So here, first of all, so I will do it in a convoluted way because of the way Agda wants it for recursion. And I have here the Python code that does the same thing, which you can study later. That might help somebody. It looks extremely unnatural in Python because it is extremely unnatural in Python. In Python, it's the search function at the top, which is the idiomatic code. So anyhow, let's see how we might do this. And we're going to write it in several ways. Okay. So here's the first one. And to see how you arrive at this one, let's start from scratch so that you will understand where this came from. So first of all, observe that the type is the one that I typed. So now I say, well, what do I do? Oh, I didn't make n is explicit, okay? So it's not implicit. Okay, so how do I type this? I say, okay, I need to define find one. Let me first see what are the arguments. So I need an n and I need a p, and that's it. And now I scratch my head and I say, well, how will I do this? Well, presumably I will do it by recursion on n, because it's about the only thing I can do. And if you had a loop in Python, the corresponding thing in the functional programming is presumably recursion. So I say, consider the cases for n. And it says, okay, how about when n is 0? What then? And I can ask Agda to show me the goal. It says the goal is that you need to produce an element of maybe fin 0. But fin 0 is empty. So I can't produce, it's not going to work. I can't start with just. It has to be nothing, right? Fin 0 is empty. I cannot find an element in the empty. So it's going to be this one. Okay? How about the successor? What do I do? How do I search now? Well, one thing that I could try would be I first see what P of 0 is. Okay? So I try, if P of 0 works, then I found it, it's 0. And if P of 0 doesn't work, I will call myself recursively. So that sounds like a reasonable plan. Yeah? You following? So we're going to test whether P of 0 is true. If it is, that's our result. But how do we do that? Now I want to say something like, if P of 0 is true, then do this, otherwise do that. Well, Agda doesn't have anything. So if I want to do it with my bare hands, I will say, oh my God, I need an auxiliary function. Consider cases, okay? Which will consider the cases. It'll say, apply to P of 0, where, and then what is this consider cases? Consider cases is some annoying function which will take the result, you see, it will take the result here, and then it'll tell me what to do when it's false, and it'll tell me what to do when it's true. So this is my plan. My plan is, here I really want an if then else, because what I really want is I want to say if P of 0, then just 0, otherwise recursive call. But because I don't know how to do an if then else in Agda, I might think, well, I will just define this function. This is a bit like, this is the Porsche business, right? It's just a Porsche, it's very fast, but you have to do everything yourself. So let's say, okay, I'll do everything myself. And it says, okay, but now please, you see how I didn't actually think about what the result here will be? So I just put in question mark. I will do this later. So, okay, if P of 0 is true, then the result is just 0. And if P of 0 is false, then what do I do? So if 0 didn't work, then I have to search the rest. And here, oh, and I can also ask Agda, do you know what this is? And it says, yeah, I know it has to be this. So I didn't have to type this type now. Because how does it know? It knows it has to be this because I typed this one. It said, well, it has to be the type of that, and I know what the type will be. And it also knew what it has to be because it's used up here. So from how it's used, it worked. Okay, so but now I need another auxiliary function, because now what I want to say is I want to say, well, make a recursive call, and then if your recursive call returned nothing, then the result is nothing. But if your recursive call is just of something, I need to increase the just of something because of the way that I made the recursive call. So this gets even worse. And after a while, you come up with this. And I'll just try to understand it. So it's saying, when I have the recursive call, it's another auxiliary function, so this is super annoying. But here is the important bit. How did I make the recursive call? So the way that I make the recursive call was like this. I started with successor of n. I'm making a recursive call on n. See? So I have, now it's a smaller n, so it will terminate. But not on p. It's not on p. It's on p composed with successor. Why is that? Because I have to make sure that P has the correct type. You see, P goes from fin. So in this case, here, this P, if I place myself here, let's put this into a hole. If I say here, what do I need? It says, well, you need, it says when you make a recursive call on find one of n, you need a predicate which goes from fin n to bool. But P, observe down here, P doesn't have that type, it has the wrong type. So what I need to do is I need to shift all the numbers by 1, and that is what this inclusion of successor does. Because successor, if I ask what is successor, successor, here, nope. There we go. It doesn't know. So it's here that is written successor, successor. Where are you, successor? Here, successor goes from fin n to fin of successor of n, you see? It shifts by 1. So you get bogged down with this business of writing auxiliary functions, and you have to think about how you're going to make the recursive call. And the way you make a recursive call is that you shift all the numbers by successor, because you've already taken care of 0. 0 is not going to work. You know that 0 is not going to work, so you want to search from 1. How do you search from 1? See, this is the case where 0 didn't work. So I need to search from 1 onwards. But the recursive call always searches from 0 to some place. So if I precompose with successor, it will shift by 1. So that's the idea. Yeah, we don't want to write code like this. I mean, we replaced a simple if then else with this garbage here. So we don't want that. So is there a better way? Yes, there are better ways. There are 2 better ways. So the second best way is to use the with. So this with business is quite useful. And let me first show you. The, where are we? Here. The example that's in the documentation, because it's a good example. And it's the filter example. So here it's a similar one. You have a predicate P, which goes from A to bool, and you have a list, and you want a new list, which is the sublist of those elements that satisfy the predicate. So how do you do that? Well, if it's empty, it's empty. But then you say, okay, what if my list, the head of the list is X and the tail is X's? How do I know whether I should include X? It's another case where you want to have a if then else, because what you want to do is you want to say, if P of X holds, then you should include X. If P of X doesn't hold, then you want to skip X. And the way you can do this with pattern matching in Agda is like this. You add here, you say, I want to consider cases on an additional value, namely on P of X. So you write in your first line, you say, oh, I want additional cases to be considered, and I want to consider what is the value of P of X. So you write this on the first line. Then the subsequent lines here, they consider the cases. So P of X is a Boolean, so they say if it's true and if it's false, what to do. So this with gets replaced by the vertical bar. This stuff here, in this case, is the same, but it need not be. And then you say, okay, if P of X is true, then I want to include X in the output list, and then I filter the rest. But if it's false, I skip X, and then I filter the rest. Yeah? So now we look at this example here. Oh, and you can have more than one here. If you want to have P of X and Q of X and R of X, you put vertical bars. Is there an example? Maybe. So here I want to do the following. Okay, the way that I will read this is like this. I will say, if n is 0, then fin 0 is empty, so I return nothing. Otherwise, suppose my n is a success. Suppose I am at successor of n, so I know that there's something in there. Okay. Then I want to consider what is the value of P of 0 prime, and simultaneously I want to consider what is the result of the recursive call. So I just do both of them at the same time. What is P of 0 and what is the result of the recursive call? Please do not think about whether this is efficient. Okay? It is forbidden for you to now think whether this is efficient. Okay? Because I'm making the recursive call all the time. It's irrelevant. Okay? It's an optimization technique to get rid of this. So let's not think about that. Okay, so now I have several cases to consider. One is, if P of 0 returns true, then I found my number, and I say, yep, you could use just of 0. But if P of 0 is false, then I go and look at the recursive call. Well, the recursive call has two possibilities. If the recursive call didn't find anything, then the result will be that we didn't find anything, because P of 0 didn't work, the recursive call didn't work, so it doesn't work. If, however, it found something, then we say, yeah, okay, we found something. But because I had shifted all the numbers by successor here in the call, I also have to shift the result by a successor. So I need to make a minor modification. Okay. This with business is quite useful when you need to, whenever you find yourself thinking, oh, I need a match statement from a camel, or oh, I need an if then else, or I need a case statement from Haskell or anything like that, it's probably with. because you just say what it is that you want to match on, and then you go and you write lines underneath with these bars, and you say if it's this and that, if it's this then that, if it's this then that, and that. Okay, so that's a good way to consider cases. There's a third way. Of course, Agda has if then else. So it could be a one-liner. Well, it seems like a two-liner because I have such a huge font. Here, let me make it into a one-liner. There we go. So this one is the one that you like the best, I'm sure. If P of 0, then the result is just 0. Otherwise, here is a complicated way to do what these patterns up here do without using any patterns, because I'm using data maybe map. So I leave this to you to detangle what this data maybe map does, what is going on. Essentially what it's doing is recursive call, and then if you get nothing, the result will be nothing, but if you get just something, apply successor to the thing in just. Okay, this one you may prefer because of your history of programming, but this one is more idiomatic in Agda. This one is more idiomatic. This is what generally will work better in more cases. And this you use if you don't know Agda. Okay. This you use if you don't know Agda, but you're very smart. So if you can figure this one out by yourself, I'm very proud of you. Like if I didn't ever tell you about width, and you just sat in front of Agda and you came up with the first solution, very good for you. Okay. Because it's not so easy to think of these auxiliary functions. Okay, so how does this get used? Well, for instance, you could use it to find square roots. So let's find square roots. So how do I find the square root of n? I say find among the numbers less than or equal to n a k which satisfies this equation. What is this equation? This equation says that k squared equals n. But it's done in a special way. First of all, k is not a number, is not a natural number. It's an element of fin n. So this 2n converts it. So I can ask, what is this 2n? Go and look. See, it's something that converts fin n to a number. 0 to 0, successor to successor. So that's just bureaucracy. And what is this equal b? Well, this equal b is here, which is this thing, which is equality of natural numbers as a Boolean predicate. And it's defined like this. 0 is equal to 0 is true. Successors are equal if the predecessors are equal, and all other cases are false. And so then you can, for instance, compute just 11. Let's compute just 11. Find square root of 121, and it says just 11. Okay, so or find the square root of 82. It says nope, nothing. Okay. Let's keep going. So last time we saw lists. This time we're going to introduce vectors. Vectors are like lists, but we want to know what the length of each, what their lengths are. So if I just say list A, then when I have a list, I don't know what its length is. Well, I can compute it. I have a function called length that computes the length of a list. But vectors are different. With vectors, we want to say vec an. So this is all lists. But this we want to be lists. Well, we'll call them vectors so that we avoid confusion, of size n. So this is going to be, so vets A takes a natural number and gives you a set. So it's a dependent type. So it's an example of a dependent type. So let's see how to define this one. It's going to be quite similar to lists. So I'm using the subscript v to indicate when things are about vectors. Maybe we can refresh memory and where are lists? Okay, so how were lists defined the last time? So a list is either an empty list, yes, or it's this cons business. You take an element x from A, you take a list of x's and you put them together. So you put a head next to the tail. And for vectors, it's going to be so now for vectors it's going to be quite similar, except that we are going to keep track of the length. So every time we have a vector, we have to write what is the type of its elements and also what is its length. So the empty vector is a vector of a's for some set A of length 0. And then if we have an x in A and we have a vector of length n, when we put them together, we will get a vector of length successor of n. Yes? This means that whenever you have a vector, its type is already going to tell you how long it is. For instance, suppose here, so here I say, I have a vector of length 3, and I define here a vector of length 3. It doesn't have to be 1 to 3, it could be 1 to 4, it's not important. And Agda is happy. If I change this to some other number, it'll complain. It'll say, nope, that's wrong. It says this should be of length 2, but it isn't, right? Because it wants 2 more elements. So I can actually put a question mark here, and it's a hole, and then I ask Agda to do it for me. I can ask it, do you know what type this is supposed to be? Which is Control-C, Control-S. Control-C, Control-S is, please fill it in if you already solved this and you know what it's supposed to be. So, and it says, yep, it's 3, because it knows. Okay. Let's see how we work with lists and how we work with vectors. So with lists, here's a list map. How do you map a function on a list, on all elements of a list? You say, well, if it's the empty list, I get the empty list. If it's a list whose head is x, and then I have a tail of x's, well, I map f on x, and then I call myself recursively. And the vectors look exactly the same. There's no difference in the code. This is the same. But notice that the types are better, because the types, you see, here they tell me that map doesn't change the length of the list. If I look at this type here, it doesn't say that. If I just look at this, I say, well, it's a function from lists to lists. I don't know what happens with their lengths. But here, I know what happens with their lengths. They get preserved. And so we see here how the dependent types are starting to do something useful. They're carrying extra information, which Agda is checking. So we can take this very far, in fact. And we will take it very far, but this is just the beginning. So now we know that when you map a vector, on a vector, the length is preserved. How about concatenation? Let's try concatenation. So if I want to put two lists together, so this is in Haskell, this is called plus plus. Okay, so here is for lists. If I'm concatenating the empty list and some other list of y's, I get a y's. If I'm concatenating this thing, well, what do? I take the head and then I recursively concatenate. Clear enough. Same code here. Magic happens. K plus m. Okay? So now Agda will check already that if I concatenate a vector of size k and a vector of size m, I will get a vector of size k plus m. How the hell does it know that? Well, it knows that because here it knows that this vector has size m, it has size k plus 1, and that this one has size k. So it knows that this one has size k, and this one has size m, and then by recursion, because what's written here, this is going to be k plus m, and then one more. So it's going to be 1 plus k plus m, but it knows that 1 plus k plus m is the same thing as successor of k plus m. It just so happens that it computes. So we are lucky. And so now we are suddenly programming in a way where the types carry information about the length. You can't do this in Java. You can't do this in Haskell, in C, C++, and there are reasons you can't do this. This kind of programming is not easily compiled to native code because you might have to calculate these things during compile time. So there are reasons. There are serious drawbacks. Nevertheless, this is a very powerful technique and it should not be just dismissed. Okay. How about list reverse? Well, okay, so here is list reverse. From the last time, we had a reversal of lists, I think, and there was an auxiliary function, if you remember, of list reverse, which I put it like this. This is how you define a little private block in Agda, and you put in some definitions, and these definitions will not get exported outside of the module, It's another way to have sort of private definitions. And the reason I need this is because later on I will need list rev. So how does list reversal work? Well, the list reversal works like using an accumulator. At least that's how I programmed it. I said, okay, in the beginning, the accumulator has the empty list. Start processing x's. How do you process them? This is maybe a little stupid. Okay, so this it's better if you call this z's. So then there is no confusion. And then if you already have the result in the accumulator and you process the entire list, then you return the accumulator. Otherwise, you make one step. You increase the accumulator, and it turns out things will work out nicely. So that's list reverse. Let's try to do this with vectors. Okay, so with vectors, the exact same thing. Given a vector, I want to turn it around. I expect to get a vector of the same size. And now it says, well, the definition is missing. And I say, okay, here's the definition. So let me uncomment this to show you where the problem is. So I just follow the same recipe as with the lists. I say, I have an accumulator, start processing the z's. Okay, here is the auxiliary function, still the same. And then I say, if you already processed everything, see here, if you already processed everything, I should return x's. So if I try to do that, what happens? Let's see. Agda says, in this hole, I need some vector of size k plus 0. But x's has size k. Unfortunately, the way plus is written, k plus 0 does not compute to k. 0 plus k computes to k, but not k plus 0. So I'm stuck. If I try to submit this, it says here, it says, nope, you can't do this because I don't see that k equals k plus 0. And this is just a simple case, and more complicated cases will arise as we do more. So here's another one. When you try to do the recursive call, it says, I would like to give Agda this thing here. It says, no, well, this is not going to work because I want something of size k plus successor of n2, but you're giving me something that is successor of k plus n2. And again, the definition of plus does not compute this. There is nothing it can do. So it says, well, I don't know why this is equal, because it can't make any recursive calls, because it needs to recurse on the first argument, but the first argument is k, so there's nothing to recurse on. So we're stuck. So we need to do something else. Okay? So what do we need to do? We need to deal with this, and we have to be able to tell Agda that these two things are equal, for God's sake. Yeah? So how do we do that? We use the identity type. The identity type is a dependent type, and last time we already saw the identity on natural numbers. So now we're going to do this in full generality. And since it's 4 o'clock, we're first going to have a break. Okay? Hvala. Ja, čakaj, sama. So we said we'd do equality. And in the first lecture, we already saw an idea of what equality would be, because we were thinking about how to define equality of numbers. And now if I ask, well, how would you define equality on any type A, not numbers, so just equality on A? Well, there is an obvious rule. The rule that you could write is this. If you have an element x of x in A, then, well, x equals x, right? Seems like a good rule to me, that should generate equality. It's going to generate all pairs, whenever I have an x equals x. So this looks like a reasonable rule for defining equality as a data type, and in fact, that's what we're going to do. So let's have a look at how it's really defined. Well, here is x equals x, okay? So let's read this. We are defining equality, which we're going to write as a triple equal sign, and then this A is a universe level, So we will just get used to the universe levels that you don't, if you just write set without any a, just set, that is the universe level set 0. It's the lowest one. So far we have always been using just the lowest one. But this one now will work for any universe level because it says given any universe level little a and a type a at that level, then we will define what it means for x to be equal to x. And that's going to be something that is a dependent type because it depends. You see, x appears here in the type. This, we are going to think of this as a type. So let's write this in a better way, more like a type. So more like a type, we would write it like this. Well, this is a type, which now is written like this. Okay. Importantly, this is a type. This change is something that you need to get used to. Things that used to be relations and predicates, like equality is a relation, you think, well, a relation, that's just something that's true or false. We're changing the view. We're thinking of a relation not as something that's true or false. We're thinking of a relation as the collection of proofs as to why that thing is true. So if I say 7 is less than 10, you should not be thinking, oh yeah, that's true. You should be thinking, what are the proofs of the fact that 7 is less than 10? So what are the proofs that x equals x? Well, this property is called reflexivity of equality. So we'll call it refl. So while here we're thinking of, oh, given any x in A, I can conclude that x equals A. So it's a fact that I have concluded. Here I'm saying I have a type, and it's dependent because it depends on A. And this type has the property that given any x, I have an element refl in the type x triple equal x. So this is the definition. So this is the passage from a relation to a type, from something that just happens to be the case, to recording, having a way to name the proof. I'm just naming the proof. It's a lot like what we did last time with less than. Okay, so reflexivity then is called refl. Where were we? Here. So now we can look at some other properties to see, let's see how this works. Okay, so suppose we want to prove symmetry. I'm not going to prove them all, but just to show you. Okay, so how do you do this? This says for any level L, for any A at set level L, if I take any elements x and y, if x equals y, if I have an element of the type x equals y, I can produce an element of the type y equals x. So this sim, it takes one implicit argument L, so I don't have to name it. Then it takes one implicit argument A. Then it takes two implicit arguments x and y. Then it takes a real argument, let me call it psi, just because I can. And then I have to prove something. So now I can see what I need to do. What I need to do is I need to produce an element of y equals x. What is at my disposal? I have the assumption that x equals y. So I can say, aha, but equality is defined as an inductive type. So I can consider cases. What could psi be? Because psi came from this type. Well, but if psi came from this type, it must be refl, because that's the only constructor. Please ignore the fact that it says instance there. I don't want to get into that now. So because equality is an inductive data type, I can consider all the cases on how I might have proved that x equals y. So I place, please consider the cases for psi. And Agda says, well, the only case is that it's a refl, but if it is a refl, that means that x and y are equal. So now suddenly y is gone, because Agda knows that if this was refl, then y and x must have been equal. To show you what happened, let me do something that will show you slightly more explicitly. If I am very careful about this, and I name my implicit arguments, and then I say, what is psi? Please consider cases. Look at what Agda did. It said, well, it was a refl where x was some x, but now, very importantly, y was an x. This dot here means this is actually some x that we have already seen. Okay? This is just Agda's way of saying, this x here is the same as the one that you just saw over here, this one. So Agda knows now that it must be the case that x and y are actually the same thing that it's calling x. Well, but then it's REFL, because x equals x. So it's a funny thing where you just keep shuffling around these REFLs all the time and you just prove everything. So let's do one more. Zeta psi. So now it says you need to prove x equals z. You have the assumption that y is equals z and x equals y. So how can we prove this? Well, I say, well, excuse me, what is this zeta? Consider the cases. And it says, well, zeta must have been REFL because that's the only possibility. So now y disappeared. And so now it says, I have to prove x equals z, but you have the assumption now that x equals z. This assumption used to be y equals z, but y became x, just like up here, y became x. So now it's y equals z. So but then I say, well, okay, but then it's psi. It should be the case that easy things are easy to prove, right?
Sorry.
Yes?
But does this mean then that any identity type is inhabited by a single?
Yes. So this is a very good question. Does this mean the identity type is inhabited by a single element? Up here, you didn't ask the same question about the top. I should ask the same question here. Is the only element of this type star? Because the only way to constructing it star. It's a similar question. The only difference is that now we have a dependency. We have the x's in there. The question does not have a very easy answer. It used to be an open question. And then homotopy type theory came along and said, no, it doesn't have to be the only one. What is true is that the type is generated by REFL. So let me give you an example. If I say that I have generated a group using generators A and B, does that mean that the group only contains A and B? No, because it contains many other elements, A squared B, A to the minus 1, right? It generates many elements. If I generate a vector space using some bases, then the vector space does not contain just the bases, it contains all linear combinations. So this generation business here, you can think of it this way. I want to have suppose you work with vector spaces and you want to have the vector space which just has 3 vectors A, B, and C. Well, you can't have that. You must have all their linear combinations as well. So the ambient forces you to put in more. And there are models of type theory where it's possible to have identity types that contain interesting things. What this is saying is not that REFL is the only type. What this is saying is every identity type has at least REFL and is generated by REFL. So if there's anything else in there, it's there because it must be there because of some model that you live in. Okay? So I don't want to get too much into this, but the answer is no, it doesn't actually have to mean that it's just REFL. However, for the purposes of this course, and because you're not even and you're not doing fancy stuff for your thesis, right? You are even what? You're doing that. But you are doing sheaves. But you're doing homotopy type theory.
Comparing set theory with homotopy type theory.
There you go. Okay, good enough. So, okay,
axial.
your world is complicated. Everybody else, it's just REFL. Okay, because that's also a consistent picture. Like if we did this in sets, it would be just REFL. So you can think either way. Okay.
So this is actually assuming the K axiom.
Agda by default, yes, but you can turn it off. Okay, so here are some other important properties that we're not going to prove in detail, which are in the standard library, but let's have a look at them. Apart from the fact that equality is an equivalence relation, reflexive, symmetric, transitive, which we just did, it has 2 further very important properties. It's a congruence. What does it mean? Congruence means a relation is a congruence if it it's preserved under some operations. And so in this particular case, it's this, that if x equals y, then when you apply a function to them, they're still equal. Right? Functions preserve equality. If x equals y, then f of x equals y. That's called congruent. That means that's the meaning of equality, is a congruence for any function. How will this be used? Whenever you are faced, if you have to prove f of x equals f of y, you can use this cong business, and f is going to fall away, and you will just have x and y. So if you have an equality where you, for instance, you want to prove successor of blah is equals successor of blah, you use cong, successor goes away. And the other one, which is important, is that it satisfies the law of substitution. So the law of substitution says, if x equals y, and I have an element of p of x, I can prove p of x, then I can also prove p of y. So this is saying I can replace x with something that's equal to it, namely y. Yes? So these are additional important properties of equality. Reflexivity, symmetry, transitivity. It's a congruence. So if something is equal, if x equals y, and then you do the same thing to them, you will get equal results. And it's substitutive. So if something holds of x and x equals y, then it also holds of y. You can transport things from p of x to p of y. That's another way of saying it. You can, if I have something in the type p of x, I can transport it to p of y along equality x equals y. Okay, how is this all used? Well, let me show you an example of how you would use transitivity. So here I have a stupid example which just tells you how to write proofs better. Suppose I know that a equals b, b equals c, c equals d, and I want to prove that a equals d. Okay, here we go. I want to prove that a equals d. I have these assumptions. How do you prove this? Well, this is just a combination of transitivities, isn't it? It's just transitivity. So I can say, use transitivity, and it says, okay, what are your two steps? Because a transitivity combines two equations. And you say, well, the first one is that a equals something. Well, but that's going to be a equals b. So here I need to prove, in the whole, it wants something that has type a equals blah, blah, blah. Alpha has that type. So I say this one is alpha. And it says, fine. Now, instead of proving a equals b, you have to prove b equals d. But that's another transitivity. And then I say, okay. It says, okay, from b, where do you want to go to? And I say, well, from b, I want to use beta, so that from b, I will get to c. And it says, yep, now you got to c. What about now? But I say, I have gamma, and so on. Okay, so this was just two uses of transitivity. In more complicated examples, this can get a bit nasty. You get these transitivities nested and so on. I mean, I can use them, but let me show you, I often use them, but let me show you another way of doing this, which is just funky definitions that are in AGDA, which allow you to argue like this. You want to prove, this is the same problem again. You want to prove an equality. So you want to prove a equals d. And these functions here, which are just combinations of transitivity and things, and this here, will work together like this. You write your left-hand side. Then you write this funny thing here. And in here, you write the reason, the proof, that the left-hand side equals the next step. And then here you write the next step. So this is starting with a, by reason alpha. So alpha, of course, is the reason is the proof that a equals b. By reason alpha, we get to b. Then by reason beta, we get to c. Then by reason gamma, we get to d, and so this is now the same proof written in a more legible way. Yes?
Would it work if they were out of order?
If what were, so what do you want me to do? Like this?
Yes.
Yes, now it's going to complain because it will say what it wants is, it wants alpha to be a proof that a equals c. But alpha is not a proof that a equals c, so it will say this doesn't work. Actually, it started checking from the end, so it first complained about the last one. Yeah. You can't just do this randomly. You really need to say, how do I get from A to B? Oh, here's the proof how to get from A to B. How do I get from B to C? Oh, by this, okay? Here's a slightly more realistic example. Suppose you want to show that in natural numbers, so this is where it's Porsche versus the truck. In Coq, this, you use some tactic and Coq says, yeah. In lean, you just say, simp probably, I imagine would work. You just say simplify, and lean goes, and it goes, and it says, yep, it's true. In Agda, you have to do everything with your bare hands. So how do you prove that A plus B times C? So notice it's not distributivity. I turned them around. C times B plus C times A. Using this reasoning, well, you start with the left-hand side, and you find the reason in the standard library that allows you to do something with this. How do I find this? Well, I press Control-C, Control-Z, and say, show me all theorems about plus. And then it gives me a gazillion theorems about plus from the standard library, okay? And now I want the right one, but I know what it's supposed to be. It's supposed to be distributivity. So I say But then, when it's distributivity, unfortunately, this is many layers of, like, this is totally illegible. What the hell is this, okay? So I say, okay, well, which one? There's this one, there's this strip R, there's this strip L. I go here, I make a hole. So in reality, when I was typing this, I had a hole like this. Oops, I don't want the question mark. And Agda was telling me, you need to prove this business here, okay? And I said, oh, I found in the library, what was it called? Oh, I already forgot. Plus this trib. Oh, this one. Let's see if this one works. And there is also one which has an R and then one that has left. So I type it in here, and I press Control-C period, which says, this is what you have, this is what you need, this is what you have. But this is illegible. So now I say Control-U, Control-C, Control period, which doesn't do anything. Then I press Control-C, Control-U twice, Control-C, Control period. Now it does something. What happened? These are keystrokes that which instruct Agda to show me what I have by calculating more or calculating less. So now it calculated a lot. And in this mess, I can see what this is. Y plus Z times X1 is Y times X1 plus Z times, is that the right one? Is that the one I want? A plus B times C, Y plus Z times X1, Y times X1, yeah, looks okay. Nope, not the right one. And so then I try the other one, and then eventually I look at this one. I say, what is this? Okay, this, I don't know why that one didn't work, but this one certainly looks simpler. Let me try to use this one. Oh, it works. But what is this? Now it wants, well, it wants to know what this distributivity was. It doesn't, oh, it did it. Control-C, Control-A did the job. Okay, so it's just doing it by itself. And so on for all of these. There's a use of Conc here, which I'm now going to skip right now because there will be another use of Conc, which will be more basic. So we'll get to it. I want to show you Conc, but not right now. So this is something that you will be practicing, how to do these chains of reasoning where you say this equals this equals this equals this equals this, and then in here you have to write proofs. Okay, I'm going to skip this example, am I? Yes, there is an example here of binary trees, which you can work through, but unfortunately I don't have time to do all of this. So let's go back to the vectors now and define reverse. You remember we got stuck on reverse? Okay, so we're going to define vectors. So let me first of all put this away, put a question mark here, just to remember what it was. Remember what it was. I wanted to say that I wanted here the result, I wanted this to be XS. However, Agda is not happy because it says, aha, I want something of length k plus 0, but you're trying to give me something of length k. That's not going to do. But now I know what to do. I know that k plus n the k plus 0 should be equal to n. So this is a case where I have an element of this type, but I want an element of that type. So I want to transport an element from this type to that type along the equality k equals k plus 0. That's a subst. So say, okay, I'll use subst. And this subst wants to know three things. It wants to know what is the type we're talking about. It wants to know what is the equality. And it wants to know what it is we're transporting. I know I want to transport this one. So this is the result that I want this one, but I don't know yet how to transport it. And now it says, well, what's the type? What type are we talking about? Oh, I have to go back. So to note what the type was, you have to observe and you say, well, what will change? You go back here and you remember and you say, what will change? Well, this bit will stay the same, that's A will stay the same, but the parameter k changes. So it's going to be a subst where the type is A of k, right? Because that's, that's A, because that's the stuff that doesn't change. And then some equality. And now it says, what is the equality? It says you have to prove that k equals k plus 0. But that is something that I know that I can find in the library. How do I find this in the library? Well, I say Control-C, Control-Z. Give me all theorems involving class. Maybe 0 would be better. Give me all theorems about 0. And hopefully, nope. Give me all theorems about plus. And now there's a bunch of them, and you search, you find, this one seems right, it's illegible, and you say, okay, this one maybe. Was it this one? Plus identity R. Nope, it doesn't want me. Plus identity R. Does anybody see what? Oh, it goes in the wrong direction. So let me show you this. So I say, is it this one? And it says, well, plus identity R goes from x plus 0 equals x. So if I apply it to k, I get, oh, k is not there, okay. So let's just say apply it to an unknown thing. So it says, see, it goes in the wrong direction. This one is something plus 0 equals something, whereas this one is the other way. So I have to use symmetry as well. So I say, I will use symmetry, and then I will use this thing. And now, can you do this? And it says, yeah, I can do this. And then it says k should be here, is this k, you see, is an implicit argument, and it's not mentioned here. So now I have to write k equals k here, and now it works. But there is another solution, which is I don't write it here, and I put an underscore here, which tells Agda, just do it, just figure out what it is. And if it's a unique thing, then that's it. That was kind of unpleasant, wasn't it? And there's another one that is unpleasant here, where you have to fix the result, which is very similar. So this is all quite unpleasant. On one hand, equality is simple, but on the other hand, this is getting kind of unpleasant. There is a better way that allows me to avoid this subs business. So let me show it to you. So let's repeat the exercise. I'm here, I want XS. I try to put in XS, you can't. Why can't I do that? Oh, it's the wrong type. And then I say, okay, so what the problem is that this argument here, it has type k, but it's supposed to have k plus 0. Agda has a special treat for you. You can rewrite here, before the definition, you write, where was this? Like this. You say, rewrite, you give the identity that you're supposed to rewrite, so it's the one from above, but now it's just, okay, so now just so happens I don't need sim, and what will happen is, it'll take this equality, and it'll transport all these arguments along it. So what this does is, I know I'm not, Okay, so what this is going to do, let me show you. I have to reload. You see now they're the same type. Without, they're not the same type. What is going on? This rewrite will take all the arguments and it will change its types accordingly to this identity. So the type of this one is this. I think I'm not explaining this very well. So does it work? Up. See, now they're the same type, so I can do it. So it's rewriting it's actually rewriting the goal, isn't it? Yes, it's rewriting the goal. There will be some examples of this in the exercises, and that's when you will actually try to understand what it is. You can't do this with the last one, so you need the subst. Whenever you have to use subst, I think it's fair to say that you will suffer a little bit, and I apologize. Okay. The next exercises, you will be practicing such things, and hopefully things will get clearer. So what is the takeaway about equality? Let's summarize, because this was kind of confusing. First of all, equality has a deceptively simple definition. It just says, whenever it's a type, whenever you have x, you can have an element called refl, and it inhabits x equals x. And this is sufficient to prove all the basic properties of equality, of which the important ones are, so let's go to this again. The important properties are reflexivity, which is there by definition, symmetry and transitivity, but also congruence and substitutivity. Again, congruence means if you see that you're trying to prove f of x equals f of y, you can get rid of f by using congruence. And substitutivity is more difficult. You have something that is in p of x, but you need something that's in p of y. That's when substitutivity comes in. Okay, maybe let me give you some, let's just go to the next thing here and discuss a little thing here that has been happening, which is the intrinsic versus the extrinsic. So it's maybe better for the lectures to explain this and not to get bogged down in intrinsic, extrinsic, technicalities of AGDA. Okay. Let's compare lists and vectors. Okay, so we had lists and we had vectors. And vectors have extra information. They keep track of the size of the vector. And this had certain benefits. What happened was that when we worked with vectors, functions such as map and reverse and concat, we automatically proved that, say, that map preserves, we automatically proved that map preserves length. So if you want to have a data structure where you control the length, it makes sense for the length to be present in the type. If you care about the length, then the length should be part of the type, just like it was with vectors, because then you will always have the information on the length. You care about it, put it in there. But we can use this in other examples. So here's another one. Search trees. What is a search tree? Well, a search tree, do you remember what a search tree is? So a search tree is a binary tree where you have some elements, and then what has to happen is here, all of them have to be, let's just do the general case. What is a search tree? Here, they all have to be less than x, and here, they all have to be larger than x, and this has to hold everywhere in the tree, okay? Not just at the root, but everywhere in the tree. That's what a search tree is. Why are search tree good? Search tree is nice because you can search. If I'm searching for a y, I compare x and y. If they're equal, I found it. If y is less than x, I go here by bisection. Otherwise, I go there. So it's a classical data structure. So it's a binary tree. what do we care about? Well, we care about the fact that it's a search tree. So we care about the fact that everybody here is less than x and everybody here is greater than x. That's really the kind of information that we should store in the type. So how do you normally implement search trees? Like, you sit down, you implement them. What will you do? Well, you will just define binary trees, and then you will carefully program your functions to make sure that your trees are actually search trees. And if you made a mistake, your function will construct something that is not a search tree. It will still be a tree, but it won't be a search tree because you mess things up. So you will have to prove after the fact, once you have already proved, once you already constructed your function. So for instance, you construct a function that inserts a new element into your tree. You will write it down using ordinary binary trees, and then you will prove separately that it works correctly. That is what I call extrinsic way of doing things. You have your data structure, and its properties are outside of the type. They are separate, they're special, right? They are not built into the type. The type is just a binary tree, but the fact that it is a search tree is an extra predicate that you need to worry about afterwards. So it's extrinsic, it's outside. Intrinsic would be more like vector. So lists are like extrinsic vectors. Lists are vectors that forgot their size. So later on you have to prove things about size if you want to know anything about them. What would be intrinsic search trees? Well, that would be a data structure that is not just a binary tree. It has to be a data structure which also has the property that it is a search tree built into it. And this is something that you will see in the exercises. You can do this using dependent types. How would you do this? One way of doing this is that you would have a tree, and you would know for each tree what is the smallest and the largest element of that tree. If your trees also carry information about what is the smallest and what is the largest element of the tree that's in there, then it's easy, because to say that it is a search tree, you say, well, the largest one here has to be less than x, and the smallest one here has to be greater than x. You know how to write down the condition. So now you're not carrying size. With vectors, we were carrying size. Now the data type will express a structural property, namely that something is ordered or that this is less than that. And the result of that will be that when you define functions on search trees, it will be impossible to define them in such a way that you will break the property. So you will be forced to correctly implement your algorithms. But I think this is a very interesting possibility, right? So what this is saying is, you see, let's step back a little bit. Okay, so it's 1948. You wear a white coat and you're programming this huge thing, and you're going bloop, 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 and you are setting separate bits. You can set your bits in any way you want, and the machine is just going to do something. You have to be very careful. You do one bit wrong, everything is wrong. You have to, start over. You don't have any help with programming. It's all very low level, okay? Then it's 1960 or 75 or whatever, and you are programming directly in assembler. So you're giving instructions to your processor. Well, now it's getting a little easier. You're not thinking directly in hexadecimal codes. You can write little words, but it's still pretty low level. You're not getting any help from the computer. So somebody invents Fortran. Fortran was a really weird thing, because suddenly you could just write mathematical formulas. It's a lot easier to write mathematical formulas that then the computer will convert to machine code, right? You're getting a lot of help. So this is about how do we help programmers write software in a good way. Types are a way of helping the programmer, because if the programmer tells me x is a Boolean, and then tries to set x to 75, I say, excuse me, you said it was Boolean, but now you're trying to do 75. This is not going to work. I helped the programmer by alerting the programmer to an error. Right? So this is a good thing. So what would be the best thing? The best thing would be that the programmer says, I would like to implement search trees. And the programmer should say this in a way that the computer will understand. And when the computer will understand that, aha, this is what a search tree is, this is what the programmer is trying to do, then the computer will not allow any bugs anymore. Because if you can tell the programmer exactly what it is you're trying to do, and the computer can check that you actually did what you promised to do, the result, once you're done, will be a correct program. That is the intrinsic way of programming, which is, it also goes under the phrase correct by construction. You're programming in a way where you can't even make a bug. So I think this is a very interesting possibility that can have some good uses. I should warn you that this is a fairly new idea, and it's with current state of development, it's difficult to program this way. The tools are not as good as, say, seasoned C++ compilers and optimizers. Your code is going to be slower because the compiler is not as good because, well, it's new. It's just like one person's project that's doing this. We are in the beginning of this, but I firmly believe that this kind of technology has a good future. So I doubt that everybody all the time will be programming in a way that makes bugs impossible. I don't think that will happen, because for a long time to come, it will be the case that you earn more money by writing buggy software fast than correct software slow. And because of that, people will actually write buggy software fast. They'll just earn more. Nevertheless, there will be cases where this is important. And this is one of the major things we're doing in this course, is this idea. This is the idea that we're going to use types, and concretely dependent types, to make sure that things are correct by the time we're done. We're done, we know it's correct. So let's also look at the other side, where you don't have everything built in. If you want to show that, for instance, remember where we said that when you concatenate two vectors, the size, the lengths get added? Well, you can do that also for lists. Right? But you have to prove it separately. So here is a proof, a separate proof, that if I calculate the length of the concatenated lists, it will be the sum of the lengths. With the vectors, this was automatic. So with the vectors, it definitely paid off, because this is extra work. I don't have to do, and there I didn't have to do this. Here is another example, which I'm not going to go through right now, but if you want to show that reversal of lists preserves length, then again you have to prove this. Whereas when we had vector reversal, well, not this one, but the one that wasn't stuck, here, it was automatic, you see? The length is intrinsic. It's built. The length is built into the data type. So by the time I define, once I manage to define reversal, I will already know that it preserves length. Whereas for lists, where are lists? For lists, well, it's a bit of work. I suspect that this can be done in a shorter way, but it was kind of nasty to do it. And the reason that it's nasty, so pay attention, the reason that it's nasty is this. You write your lemma that length of reverse equals length. See? Length of reverse. You write this and you say, okay, let me prove this. And then you go here and you say, how am I going to do this? And you ask Agda to calculate a little bit, and it says, okay. Yeah, it calculated a little too much. Okay, calculate less. Well, now it's kind of stupid. But then I go and look at the definition of list reverse. And when I look at the definition of list reverse, it says, hey, list reverse is just a call to this auxiliary function. So what will happen? Well, now I will have to prove something about this auxiliary function. So I go and I stare at this and I say, what is it that I need to prove about this auxiliary function? And after a while, And this is the difficult part. My function, I would like to prove something. But in order to prove the thing that I want, I need to prove some other statement that I still have to figure out what it is. And this is the difficult part. You are searching for the correct invariant in a recursion. You are searching for the correct property of the auxiliary function. This is the difficult part. You will face this in the exercises in your projects. What was the thing that it turned out after some thinking? The thing that I had to prove was that this list reverse has the following property. The length of the list that is returned by the auxiliary function is the sum of the two lengths. And once I knew that this was the thing I had to prove, then it was a little bit easier. And this was comparatively easy compared to figuring out that this is what I need. And I said, please use the fact that this length reverse works. And I said, okay, I can do that for you. I can do that for you. I can do that for you. Because it's almost 5 o'clock, I'm just pointing out the important fact is this. When you do the reversal of vectors, it was not simple, but simpler than this extrinsic way. Now we have, you see, why is that? When you're programming and proving at the same time, everything happens together, so all the information is there. If you are first writing your code and then you're proving that it's correct, you have decoupled things, and you have to, when you're proving, you kind of have to figure out, oh, what was it? How did I program this? You're almost redoing all the work again. Just this time around, you have to do it with all the properties and everything. So I would say both ways of dealing with things are valid, but this second one, where you prove things afterwards, you really want some help from some powerful tools. Because if you have to do it with your bare hands, it's not as nice. Okay, one last thing before we finish, which is the following exercise. If I have a list, I may wish to ask the question, I have X, which is an element in A. I have L, which is a list of A's. Well, somebody's going to shout at me for doing this. Okay, so like this. And I can ask, is X an element of L? Your first thought is going to be, oh, the answer is true or false. So element should be a function into booleans. It takes an element and a list and it returns a boolean to tell me whether something is in there or not. Yes, this is possible, and we discussed this, and this means that I am representing a relation, namely element, using a boolean predicate. It's fine. But let's also do it in our style, where I say, I don't think of this as true or false. I don't want to think of the value of this as true or false. I want to think about all the ways of proving this. How do I prove this? And then I write down rules for proving that X is an element of a list. Here they are. X is an element, so what are the possibilities? One possibility is that X is an element of the list because X is the head. If X is the head, if it's the first element, then it is in the list. And I will call that, this is a proof with the constructor called element here. The other option is this. If I know that X is in a list, then it will also be an element of the slightly longer list in which I attached another Y to my X's. So these are the rules for searching the elements through a list. So either it's the head or it's in the tail. Yes? This is how you can define element. How would you define an element hood for trees when you have search trees? For search trees, the cases will be, my element is at the root, therefore I found it, it's in there. Then the second constructor will be, if my element is in the left subtree, then it's in the entire tree. And the third constructor will be, if it's in the right subtree, then it's in the entire tree. So there will be one more. And then you can write proofs, for instance, that 5 is an element of this. And Agda can do this using Control-C, Control-A. It says, if you think about it, this really corresponds to the position of where we're going to find 5. Because it's going to be there, 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 there. And when we hit 5, we'll say here. So it's really just the index. It's a funny way of writing the index of where 5 appears. You can also prove that something is not in the list by showing that if it were in the list, we could prove false. And this is something that Agda can also do using Control-C, Control-A. You just keep pressing Control-C, Control-A. And down here, it comes to a case where it says, this is impossible. It gives you the funny parentheses, and it's done. So this is a good example to try at home. You do it like this. And they say Control-C, Control-A. No? Oh, no, it doesn't want to do. Wow. Maybe I have to write it with my bare hands. I say, in there. Oh, no, I'm sorry. I need the proof P. Okay, I say, suppose P prove, what if P proved that 4 is an element of this? I say, well, what could P be? Control-C, Control-C. It's like this. What could P be? It said, well, P could not be here because 1 is not 4, so it had to be the rest of the list. And I said, well, okay, but then what happened then? And it says, well, but then because 2 is not 4, it had to be the rest. And I say, okay, but then what? And then I say, well, then it had to be somewhere else because 5 is not 4. And I keep doing this. I keep asking Agda, what are the possibilities? And now Agda arrived at the case where it's looking at the empty list. So, and I said, what could P be? And Agda says, no, it couldn't be. No more possibilities. We're done. And then here will be, okay, so we really don't have time for this, but if you have the time, I would suggest that maybe you look at some of these examples, maybe even before tomorrow, if you have the time. So, for instance, you want to prove things like this. If X is an element of a list, then it's an element of the reversed list. And this, again, is going to require some lemmas, auxiliary lemmas that you get here. I think there's another one here that if Z is in Y's, then it's in the X's plus Y's. And if Z is in X's plus Y's, then it has to be in one of them, and so on. See? These examples are, okay, so this is just a small remark down here. You can read. These examples here are, okay, let me finish by saying something that will apply to the rest of the lectures. The way that this course is structured is that you're going to do a class project. Why? There is a deeper reason other than I don't want you to write stupid exams. I don't believe that anybody can learn this stuff by watching me, okay? It's impossible. You have to do it yourself. You have to invest some time. You have to sit in front of it. It's like watching football or watching somebody program. You're never going to be good at football by watching it. You're never going to be good at anything without practicing it. But this in particular here is a case where you will only appreciate the little points that I'm trying to make once you hit them. So we'll try to make this more interactive. So I think the conclusion from today's lecture is that I'm too slow because I'm trying to do too many details. And I'm pretty sure, please give me feedback, I'm pretty sure it is impossible to actually absorb all these details in the 3-hour period. So I'm going to try next time to focus more on the ideas and the overall picture. And I'll just have to try, we'll just have to trust you that you will put in a little bit of effort. And I will say now today for the 10th time, try to do things. When you get stuck, ask. Because when you're stuck and you don't know what to do, that's when your brain will listen. Your brain is tired now. It can't listen. It wants to go home. When you're trying to do, at that moment, Discord, I'm stuck on this piece of code. Show us the code. This is what you need to do. That's when your brain will learn, okay? And do it with your friends, cooperate, do it together. That would be my advice. So I think I learned from today's lecture that next time I can't possibly go into so many details. I think my and your time is better used if I try to explain the philosophy and the techniques and not so many details. But look at the details, because that's where the real knowledge is. Thank you.